This is the UKMT pink Kangaroo from 2024. Let's just go into it. We can kind of divide this by 10, this by 10, or just kind of factorize out to be 10 times 2 and 10 times 0.24. And of course, this cancels, it's 1 over 10 times 10, which is 1 over 100, which is A for our first answer. We can draw some lines here, like down here and across here, and we'll end up with 1, 2, 3, 4 kind of regions that are the same. So the ratio of black to grey is 1 to 3, we can just see here. The other, it doesn't really matter, it's just the same thing over and over again. So therefore it's 1 to 3. Number 3, palindromic numbers, fine. To be a multiple of 6, you have to be even. So we can't use 9 something 9, because that's not an even number. So the highest thing we can try is 8 something 8. Now, to be a multiple of 6, you have to be even, but you also have to be a multiple of 3. Multiples of 3 have a digit sum that's divisible by 3, so we can't put a 9 here because that would add to 25. But if we put an 8 here, that's 24, which is a multiple of 3, so therefore it's divisible by 6. Here, the interior angle of a hexagon is 120. Just go into the UKMT knowing that, obviously. This is 90 up here, obviously. Now, the key thing is that that's the center of the square, so this is 45 and 45, which means here's just a quadrilateral. 360 minus 90 minus this would be alpha, and we'll end up with the answer of alpha here. Number 5, a rectangle, and the prime numbers all the way around, but the prime number has to be repeated here and here and here and here, right? Because it's a rectangle. So we can actually just think that we want these two primes to add to make 20. And of course, the most obvious things to do that are 13 and 7, which multiply to make an area of 91, and that ends up being the highest. If you try and go further, closer to 20, like doing something like, I don't know, 17 times 3, you just end up making a much smaller number. You want to be as close as 10 times 10 as you can, which is by doing that, because 11 times 9 doesn't work, because 9 isn't prime. Okay, we have PQRS in these squares here, so one way to do it is do PQRS, and then we have to try, R and S have to be here, because otherwise this box wouldn't have a P and a Q in it. And so P and Q over here, but specifically they have to be swapped over as well to make this middle box have all 4 as well. Now this actually ends up being the only way to do this. Basically, you have to have a letter here and its corresponding letter down there, and likewise here and here, and likewise here and here and here and here. You can't mix those around in any way, because otherwise you kind of mess with the middle box and cause it to be wrong. So this is the only way to do this, except what we could do is we could just swap the letters for each other. So if you imagine just having like letter 1 here and here, and 2 here and here, and 3 here and here, and 4 here and here, there are 4 choices as to what you make letter 1. PQRS, and then 3 choices to what you make letter 2, and then 2 choices to what you make letter 3, and then 1 choice for what you make letter 4. So 4 times 3 times 2 times 1 is 24, and end up with the answer of B. Here, we want to go kind of starting somewhere in and out and in and out and in and out and so on. How do we do that in the least possible journey? Well, we don't repeat the longest journeys. So if we start here on this edge, we'll only have to do this journey once. And if we start here, if we end over here, we'll only have to do this journey once. So we can do 3 plus 2 plus 2 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 2, and that will draw the entire thing, repeating the least distance, and that turns out to be 15 in total. Now, this is an equilateral triangle, so we could do a half times 4 times 4 times sine 60. Sine 60 is root 3 over 2, and you end up with 4 root 3 as the total area of this triangle. Just know your exact values makes everything very quick. Now, that means, because this is a third of the entire shape, that means the entire shape is just 12 root 3, which means the side here must be 3 root 3, because 4 times 3 root 3 is 12 root 3, which is cool because, and there's a couple of different things you could do here. I think I typed up something that I later thought was actually probably a quicker way of doing this. This triangle, you could also say is a half times this length here, but we know that's 4 root 3. So the 4's cancel, and you just get a half times this is root 3. Which means this must be 2 root 3. And if this whole thing is 3 root 3, then this bit there is root 3. Alternatively, you can say that this length is 2 here, and then you can do the area of the trapezium must be equal to this again. So that's going to be this plus, if you call this x, times 2 divided by 2 is 4 root 3. And you can work out x as root 3 that way as well. Different options for doing that, I guess. This is the question that tests whether we looked up 2024's prime factorization before we did the test. I did, it's that. And now we just have to sort these primes into some reasonable way to make the ages of 3 people. So make the youngest one 2. You've got 2 2's left over. You could double both of these, and that makes that 2, 22, and 46, which seems just about reasonable. So yeah, 46 will be the answer. You could also note that there's no way to make 48 here, because you don't have enough threes, and there's no way to make 50 because you don't have a 5. So actually, the moment you have this, 46, I think is, oh no, 44, I guess. 44 you could go with, but then you only get 2 people because you need all of this. No, you don't. Hang on, 2, 44, and 23? No, what am I doing? Um, oh, they're all even numbers. Yeah, so this is the only one that works. I didn't even read that. That's fluky. Um, yes, the other option I just came up with was 2, 23, and 44, but they're not even. Okay, cool. So that is good. That's correct. Number 10, sum of the digits of the positive integer n is this. Now, if you go from an n to an n plus 1, almost always your digit sum increases by 1 because you go from like 13 to 14, and the digit sum goes up by 1 because this number goes up by 1. So how did you get your digit sum to go down? In fact, how did you get it to go from 3 times what it was? Well, you go from like 9 to 10, right? So this is 9 times the digit sum of this one. So it's when you flip over to the next kind of digit. So 19 to 20 will work, but this gets you a digit sum of 10 to 2, so that's 5 times, not 3 times. And then eventually you find this one here, 12 to 4. So the answer is the digit sum of 12. 11 then, so ratio of black to white is 7 to 1, which means if you put the white circle in the black bit, that means there's 6 parts of it left over. So there's only 6 parts now, so it's just 7 to 6, and that's about as simple as that. This is an equilateral triangle, so angle 60, 60, 60, which more to the point means that these trapeziums are isosceles trapeziums because it goes 60, 60, 120, 120. So they're kind of isosceles like this, which means this length is the same as this one, so that's a 3 down there. And likewise, this is a 2, and that's a 6 over there. The next thing I did, and I don't know whether there's an easier way to do this, there almost certainly is, but I just drew a line this way and said that this angle is also 60 because these are all parallel, I should have said, to the original sides. And you can do a bit of SOHCAHTOA here if that's 60, knowing cos 60 is a half, to work out that this little length here is 1.5, which is super useful because then so is this length down here, and this length here is 6 because it's the same as this. This all adds up to make 11, and there's just 11, 11, 11, and you end up with a perimeter of 33. Probably easier ways of doing that. This is one of those questions where you just want to try stuff. So I just put the 2's kind of here to make 4, and then just put these 1's here. And I didn't know this would work, but I just wanted to try it. To make a 10, I need another 5. I can't put the 5 here because then this is all messed up. So the 5 has to go here. It doesn't matter which one it goes in, obviously, because it doesn't affect anything else. So now just throw a 1 in here and a 1 in here to make that whole thing 10. And then here we just need another 3, so that needs to go there. 2 times 3 is 12. Over here, we just need another 2 and a 1. That can go anywhere at once. And over here, another 4 and a 1. And that can go over at once. Times the grey ones together, and you end up with 40. Because of all the 1's helping you out. The sides of squares are integers. The difference between the two areas is 19. The two square numbers with a difference of 19 that aren't very difficult to find are 81 and 100, which means the side lengths are 9 and 10, which means the perimeters are 36 and 40, which add up to make 76. Not a difficult question. Number 15, Molly has cards numbered 1 to 12. Here's an octagon. Now, the first thing I did was notice which numbers here are just not anywhere on here, and I saw 4 and 10 weren't. So 4 and 10 have to be somewhere on this. They can't go next to each other because then they add up to make 14. So just put the 10 here, and then just, again, just like 2 questions ago, just try stuff, right? I kind of went in roughly size order. A 2 can be used here to make both these multiples of 3. And then I just went around, right? So 5 could be used here, that will work. And then 5 plus 7 will work to make a 12. And then 7 plus 11 will work to make 18, and then just keep going around. Just hope you can make it work. 1 and 12 make a multiple of 3, sort of 1 and 8, instead of 8 and 4. Amazing. And you're left with these here. You could have just obviously pointed this out because these are just the multiples of 3. So there's nothing that they can go next to in this game other than each other. And so, of course, you run out of time when you try and put any of these down, you just run out of other things to put in. So it's kind of also quite obviously the answer. Anyway, number 16, just start by saying, this is true to start with. Essentially, we want 4 of these to be true. We want 4 of the 5 to be true. So we're just trying to, or of course, 4 of the 5 to be a lie. So we're just trying to make that happen. So if we say this is true, okay, so he lied yesterday and he'll lie tomorrow. So he's telling the truth today, essentially. So that's fine. So I'm telling the truth today and I'll tell the truth tomorrow. That's a lie because he is telling the truth today, but he can't possibly be telling the truth tomorrow because that's not how this works. This is divisible by 11 because we previously looked up the prime factorization. Yesterday was Wednesday could well be true if it's Thursday, but tomorrow won't be Saturday if that's the case. So we end up with 3 truths and 2 lies, which is not how this should work. However, I can turn this true into a lie if I just pretend that like today is Saturday, that then they'll both be lies. And then I can also turn this one into a lie by just saying this is one of his lying days. Because none of this is broken by that. Because I'm telling the truth today is still a lie. But it was a lie previously because of this bit, because now it's because of this bit. This is still true because it's always true. And so we can fashion all four of those into lies. And this is the one that he didn't actually make because today is his lying day, so he can't have said that. Question 17 then. He's rolling a dice 24 times, but he needs the numbers 1 to 6 to come up at least once. So let's just say that they do. Those sum to 21, and he's got 18 rolls left. Now, how can we use these 18 rolls most efficiently? Well, we can just do some trial and error, right? He needs more ones than any other number. So let's just say to start with, he gets 6 ones, which means at most he can have 5 more 6s, 5 more 5s, and 2 more 4s. Let's just add this up. So 6 plus 30 plus 25 plus 8 gives us a total of 69. And then if we just try 5 ones, which means we can only have 4 6s, 4 5s, 4 4s, and an extra 3, because we need all these to add up to 18, right? The number of rolls, 5 plus 4 plus 4 plus 4 plus 1 is 18. Those are 66. So it's gone down. So I think that means logically going down in the ones from here just makes it worse and worse. I haven't proved that, but this is a math challenge, so I'm just going to assume that and move on. But what about going up in ones? So what about 7 ones? Which means you can have 6 6s, and then they only need 5 5s to make it all out to 18. And this is 7 plus 36 plus 25, and that makes 68. So again, I'm going to use this logic that going upwards is also going to make this worse. And this is probably the optimal solution, and 21 plus 69 give me 90 in total for my answer. This is a gorgeous question. So n factorial is just 1 times 2 times 3 and so on to n. So you look at this and think, well, this is 47 factorial, right? The 46 and the 45 and the 44 are missing because they're broken down into their primes. But 47 is the highest number because it's just a prime number. So, okay, well, where did the 17 coming from? Well, you get 1 from the 17 and 1 from the 34 because that's 2 times 17. So, okay, the obvious answer is 2. Except then you look at this piece of information, 13 to the power 4, conspicuously not rubbed out. How is that helpful? Well, think about where you're getting 13s from. You're getting 1 from a 13, 1 from a 26, 1 from a 39, and 1 from a 52. So this thing must have gone up to 52. So why are they all missing? Well, because 48, 49, 50, and even 51, because that's 3 times 17, are all being broken down. And so is 52. But you can't then go to 53 because 53 is prime. So this must be 52 factorial because of these 4 13s. And if it is 52 factorial, that means you get another 51 in here, which breaks down to a 17. And so you end up with 3 17s in total. Question 19 then. So if you kind of round this out and close it up, it will look a bit like this. This is not what it looks like because this has got more sides to it going around, but it makes it easy for us to see. Anyway, all I need to do to work out the distance between J and K are the top point and the bottom point. So I just need the distance vertically. Of course, this distance here is just 1 because that's the side of the square there. And so what I really need is the height of these 2 triangles here. And those 2 triangles are equilateral triangles, like 1, 1, and 1, because, of course, the square length is 1, and these are all 1s. So it's 1, and 1, and 1. So I want the height of this. So all I'm going to do is work out the base of this is root 2, because it's a 1, 1, root 2 triangle. So this half here is root 2 over 2. Just half of that. And then, of course, I can do Pythagoras to work out the height. This is just a quarter, which makes this, sorry, no, it's not, it's a half because it's 2 over 4. So 1 minus half is a half. Root it for 1 over root 2. You can rationalize this for this if you want to. And then, of course, I just need 2 of those. 2 of these is just root 2. And then the one in the middle gives me 1 plus root 2 as the answer. Some cubes making 27 to build a cube. First thing we'll notice, I mean, there are 54 surfaces here. It's just 9 times 6. So we want 18 of them to be black. Now, what we can notice is that there's 1 cube in the middle that is not being used for any of the surfaces. So we can make that whatever color we want to maximize our blacks or minimize them. If we want to maximize them, we'll make that middle cube black. And if we want to minimize, we won't. The other thing we'll notice is that some cubes matter more to the surface area than others. This cube here, half of its sides matters to the surface area, whereas this cube here, only one of them does. So if we want to minimize the number of black cubes we're using, we want to make the black cubes the corners, because each corner denotes or gives us 3 sides, and we only need 18. So if we just make all 6 corners black, that will be 18 squares shaded in black, and that's a third of the shape. So 6 blacks will be the minimum we use. If we want to use the maximum number of blacks, we'll put one right in the middle, And then we'll also make these ones black because they only contribute one side. So that's 1 in the middle and 6 in the middle on the edges here. That's going to be 7 black ones in total. And we only have 6 colored faces. And we need 18. So now we'll focus on these kind of ones, which donate 2. We need 6 more of those because 6 times 2 is 12. Add it to the 6 we've got before makes 18. So therefore 6 plus 6 plus 1 is 13 blacks as a maximum. Difference being 7. Question 21 I have done in an absolutely ridiculously stupid way. First thing I said was that let's just say that her walk is 2 hours long. And then, because that just helps out with the first bit, she walked half the time, so that's 1 hour walking at 2 kilometers per hour, so she did 2 kilometers. She then walked half the total distance, so let's just call the total distance D. I can't make up another thing for that because that might ruin everything. So I'm just going to call D the total distance. She did half of that, so using this formula here, over T1, so that's just how long she walked for 3 kilometers per hour. Then she did the remainder of the walk. Now, how far has she got left? She's got D minus half D minus 2 to do. That's the distance she got left. And that equals 4. And then you divide that by T2, I'm just saying, which is the second amount of time she walks for. And now let's just do some algebra. I'm just very happy that my algebra was very strong. By the way, T1 and T2 add up to 1 because I made up that the total time was 2 hours. And then she walked half of that time, which is, of course, 1 hour. So that means the other 2 times add up to 1. I'm very confident with my algebra, so I'm pretty sure this is just going to go okay. I multiply that oversimplified, and of course multiply this oversimplified, and then I think I'm just going to put this T2, I'm going to say it's 1 minus T1 to make this. But then I said, I guess, that T1, what am I doing here? T1 is D over 6 from this equation. And now I can just solve this for D. Just doing some algebra to get D is this. It's not a nice number because I just picked a random thing to start. So D is this, which means, of course, that if I halve that and take away 2, I'll end up with 4 lots of T2, which is the second amount of time she walked for at the end here. So again, times that, or halve that and take away 2. This is 28 over 14. That makes 8 over 14, which is 4 over 7. Cancel the 4s, you get 2t as a 7th. So you get T2 as a 7th. So T2 is a 7th of the walk. Sorry, a 7th hours. She walked for 2 hours, so that makes it a 14th of the total time. Integers 1 to 25, this person wants to remove a few and split the remaining so that they have products that are equal. As soon as you see products, you need to think prime factors, because that's how we really make products without actually having to multiply them together. So the numbers written as prime factors are 1, 2, 3, 2 squared, which is 4, 5, 6, which is 2 times 3, and so on. And what I did at that point, all the way up to 5 squared, which is 25. At this point, I just counted how many 2s, 3s, 5s, 7s, and so on were in this group, and it's this. That's how many 2s. It's a laborious process, but you just count it up super carefully. And now, if you want to split these into 2 groups that multiply to make something equal, you just need an equal number of all these primes in each group. Now, 13, 17, 19, and 23, you can't have an equal number of those in each group because there's only one of them. So she must remove a 13, a 17, a 19, and a 23. And also, she must remove a 7 because that way we'd get up to 2 sevens. Except she can't just remove the 14, because the 14 is actually a 2 times 7. And then she messes up this here. So I think she should just remove the 7. So she must remove all of those and a 7, but I think actually the 7 she needs to remove in order to not mess with any of the other numbers as well. So okay, if she does that, she'll end up with this, and this is perfectly easy to split in half. You can put half the numbers like this and half the numbers like that, and great. We'll have the sum of the numbers removed is obviously this plus this plus this plus this plus this, which is I think it's going to be 81. However, at this point, maybe we should just check that you can actually, because when she's distributing the rest of the numbers, she's not allowed to distribute them just as 2s and 3s and 5s. She needs to distribute them as the actual numbers. So maybe we should just check that we can actually distribute two groups to make these. So okay, I started with the 7s and the 11s. So we've removed the 7, remember? So we can only use the 14 maybe and the 21. That gives us an extra 2 over here, an extra 3 over here. So let's split the 7 out, the 11s out. If I put 11 there and the 22 there, that gives me the extra 2 that I needed over here to balance these out. But I still have the extra 3 over here. So let's just put the 3 here, right? And now let's balance the 5s. I need 3 5s over here, so 5 and 25 will do, and 3 5s over here will be 5, 10, and 15 maybe. Sorry, 10, 15, and 20 maybe. I didn't use the 5 because I've used it, of course, yeah. So 10, 15, 20 are the remaining ones left. Now that gives me way too many 2s over here. 1, 2, 3 of them. So let's balance that out by putting the 8 there. And now let's balance the 3s. Currently I have 1, 3 over here, and 1, 2 over here. So I need an extra 3 over here. I can't just put a 3 here, so I need to put the 6 here, which gives me an extra 2 over here. So let's put an extra 2 over there. And now I think everything is balanced, and I've managed to get the 5s, 7s, and 11s all done. And have I done the 3s? I haven't done the 3s yet. I've got 1, 2, 3s over here, and 1, 2, 3s over here. So, okay, I need 3 more 3s in both groups. So I think just the 9 and the 12, that's 1, 2, 3 of them. And over here, therefore, the 18 and the 24, that's 2 in there and 1 in there. Now this means I've got 2 2s in there, and then 1 2 and 3 2s. So there's too many 2s over here. And counterintuitively, I'm going to put even more 2s over here. This is another 2 2s. So now there are 4 too many 2s over here. But luck would have it, the remaining number is 16, which is 4 2s, and so this is separable. The 1 doesn't care where it goes. And so this is possible, and if we just remove those numbers, which actually add up to 79, apparently, then we are all good to go. 23, we've got a circle split into 20. And we want chords that are shorter than the diameter, so we're not allowed to use this, but longer than the radius. So we want chords like this. But like, where do you stop? Is this longer than the radius? On this side over here, this is a fifth of the circle going from 1 to 17. You can just count the spaces, but this is a fifth of the circle. So if you go to the center and out again, this is 72 degrees because 360 divided by 5 is 72. But of course, this makes this not an equilateral triangle because of the 72. But it also makes this longer than R because the longest side of a triangle is opposite the biggest angle, which is this. So therefore, this is bigger than R, which means this is an acceptable chord, but the next one won't be. The next one will actually make an equilateral triangle, which is equal to the radius, so therefore not longer than. So we're allowed this, not 11, because that's equal to the outer, and this, and this, which I believe is 12 of them. So there are 12 points from each one. 12 times 20 gives 240, but every single time you count a chord, if you do it this way, where you just count from every single starting point, you're going to count every single chord twice. For example, later I'll start at 17 and count the 12 from there, but that doubles the one that I counted there, so we just divide by 2, and we get 120 in total. This question is actually unbelievable. I have no idea how you're supposed to, in any reasonable time, come up with this. Basically, if one line intersects 11 lines, that means there are minimum 12 lines. So what I'm going to try and do here is just draw a picture with this in it with 12 lines, because then I know it's possible to do it with 12. So let's just draw a line and make it intersect 11 other lines, like so. Right? Now, clearly this is wrong because there's nothing intersecting 5 lines and nothing intersecting 9. So what I'm going to do is I'm just going to group the lines together a bit. Sorry, that's 11 lines there. Group the lines together a bit, and then put another one going diagonally through everything. Because the key to this question is, it doesn't say exactly one line intersects 11. It just says one of them does. So now I've got 2 lines intersecting 11 other lines. Right? Because basically the moment something is non-parallel to the others, it intersects all of the others, because of course the lines continue forever, so they will intersect it somewhere. So okay, this is my picture now, except I'm not satisfying this or this. I'm satisfying this twice, which is fine, but not this or this. So let's pick up these 3 lines. Notice how all these lines, these vertical ones, are intersecting 2 lines. All of them. So if I pick up these 3 and just make them horizontal, all of these will intersect 5 lines, which means this is now satisfied. So the only thing I need to do now is have one of them intersecting 9 lines. And then we look at this original horizontal line I had, and because of these 3 removed, it now does 1, 2, 3, 4, 5, 6, 7, 8, which is annoying, but okay. I think all I need to do to fix it is, remember, we're not relying on how many intersections these horizontal ones have, which I think also have 8. If I just turn one of them slightly, it will still intersect this one every time, so that's still 11 on this one originally because it's not parallel. But it will now touch this one down here, thus meaning this one has 9. This one still has 11. All of these still have 5. This one now has 9, and so this construction is okay. And 12 is therefore a possible thing to draw. Absolutely ridiculous question. Okay, m and n are integers with coordinates mn and nm, so it looks a bit like this. M is less than n, so this I think is a valid picture. O is 0, 0. Triangle OPQ looks like this. And we want the area equal to be this. Okay, the midpoint of this is that, because you just average the x's and average the y's. The area of this triangle is just going to be a half times base, which I'm going to call this, times height, which I'm going to call this. So what is this distance? Well, if this is the coordinate this, that means this distance across is m plus n over 2, and this distance up is m plus n over 2, which means this triangle is isosceles, and it's right angled, of course. So this distance, just doing Pythagoras, the classic 1 root 2 triangle exists. So if this is m plus n over 2, n plus n over 2, this is m plus n over 2 times root 2. It's just a scale factor. We can avoid doing Pythagoras by just scaling up the 1 root 2 triangle by this factor. So that there is the distance there. This distance here, more Pythagoras required. We're just going to find the distance across, which is n minus m, and the distance up, which is n minus n, and square them and add them together at square root to find this distance. If you expand all the stuff out and cancel a bunch of things out, you'll end up with this, I think. Will you end up with that? How have you got this? N squared plus n squared. Because it's just, you're an idiot. It's because it's two lots of these things, and when you root it, you get root 2, and then the square cancels, and you get this. Okay. So then the area of this triangle is a half times this times that. Now, that equals 2024, according to the question. A half times a half is a quarter. Root 2 times root 2 is 2. So all that cancels down to a half, and you just need to double this. This is where, at some point, you needed to have learned that 2024 is 2 cubed times 11 times 23. And then the extra 2 comes from the line, the 2 that's coming over here, and we get this here. Now we have two things multiplying to make this. This one is bigger than this one, because it's a plus, not a minus. And also, both of these things are even, because if you add them up, you just get 2. Sorry, both these things are either even or odd, because if you add them up, you get 2n, which is even. And the only way to add up two numbers to get an even is if they're both even or both odd. So both of these things are even or odd. So when I'm sort of splitting out these numbers into two piles to try and make this, I need to make sure there's at least 1, 2 in both of them. So this is a valid construction. This thing times this thing is the thing, I think, 4048 that I'm trying to get, right? And they're both even, so that's fine. You could donate another 2 over there to make this pair, or another one to make this pair. You can instead donate the 11s across now to make this pair, or this pair, or this pair. Everything is even in both ones, which is great. And now, it's tempting to think we could donate the 23s across, but actually, we've essentially already done that with this group. It will just be the same thing backwards. And if you put them both across, then we've done that already. It's this group. And actually, it turns out that this is the only way of doing it. So there's 1, 2, 3, 4, 5, 6 pairs, and that'll be our answer. Thanks for watching, and I'll see you next time.